If someone asked where the universe ends, you'd probably say it doesn't. But there's a number in physics that says otherwise. When scientists calculated the mass of the observable universe and asked how big a black hole made from that mass would be, they got a radius almost identical to the age of the universe itself. That number shows up again in how fast the universe is expanding. And that's a problem because those are exactly the numbers you expect. If the universe isn't outside a black hole but inside one. To understand why this number matters, we need to understand what it means. In 1915, Albert Einstein published his general theory of relativity. The theory described gravity not as a force but as curvature in spacetime itself. Massive objects bend the fabric of space and time around them. And this bending is what we perceive as gravity. Einstein's equations were notoriously difficult to solve. They involved complex mathematics describing how matter and energy warp the geometry of spacetime. Einstein himself struggled to find exact solutions. But Karl Schwarz, a German astronomer serving on the Russian front during World War I, found one. While stationed in the trenches, he derived an exact solution to Einstein's field equations. This solution described the space-time geometry around a non-rotating spherically symmetric mass. The solution contained something unexpected, a critical radius. If you compressed any amount of mass inside this radius, something strange would happen to spacetime itself. Time would slow down at the boundary. Light could not escape. The object would become what we now call a black hole. This critical radius became known as the Schwarzschild radius. For the Sun, the Schwarzschild radius is about 3 kilometers. The Sun itself is 696,000 kilometers across. So the Sun is nowhere near being a black hole. For Earth, the Schwarzschild radius is about 9 millimeters. For the Moon, it's about 1/10th of a millimeter. The Schwarzschild radius grows linearly with mass. Double the mass and you double the radius. This creates an interesting property. As black holes get more massive, they actually become less dense. A stellar mass black hole formed from a collapsed star cram. The average density is incomprehensibly high. But a supermassive black hole at the center of a galaxy with millions or billions of solar masses has a much lower average density when you calculate it across the volume enclosed by its event horizon. A black hole with the mass of about 140 million suns would have an average density equal to water. A black hole with the mass of about 11 billion suns would have an average density equal to air. The relationship is mathematical. Density equals mass divided by volume. Volume scales with radius cubed. But for a black hole, radius scales linearly with mass. So as mass increases, density decreases as the square of the radius. This means that if you had enough matter distributed across a large enough volume, even at very low density, the Schwarzschild radius could theoretically exceed the physical size of the region. And this brings us back to the universe. The observable universe has a radius of approximately 46.5 billion light-year in co-moving coordinates. This accounts for the expansion of space over time. The universe is 13.8 billion years old. But because space itself has been expanding, regions that emitted light 13.8 billion years ago are now much farther away than 13.8 billion light-year. The mass-energy content of this observable universe can be estimated. We know the critical density required for a flat universe from cosmological measurements. It's approximately 8.6 into 10^27 kilograms per cubic meter. This comes from observations of the cosmic microwave background, the distribution of galaxies, and the rate of expansion. Multiply this density by the volume of the observable universe and you get a total mass of approximately 7.7 into 10 to the power of 53 kg. Some calculations use slightly different values around 8.8 into 10 to the power of 52 kg depending on whether you count only baryonic matter or include dark matter and dark energy in the equivalent mass-energy calculation. Now apply Schwarzschild's formula to this mass. The Schwarzschild radius comes out to approximately 13.7 billion light-years in some calculations, or up to 37 gigapax in others, depending on the exact mass used and how you define the observable universe's boundary. But here's where it gets strange. The Hubble radius, which is the speed of light divided by the Hubble constant, equals approximately 14 billion light-year. This is close to the light travel distance since the Big Bang, and it's remarkably close to the calculated Schwarzschild radius for the universe's mass. This coincidence was first noted by physicist Raj Pathria in 1972. He pointed out the structural similarities between the observable universe and the interior of a black hole. The universe has a singularity in the past, the Big Bang. A black hole has a singularity in the future, the point of infinite density at its center. The universe has an event horizon of sorts, the cosmological horizon beyond which we cannot observe. A black hole has an event horizon beyond which nothing can escape. The mathematics looked eerily similar. There is a connection here that goes deeper than coincidence. The expansion of the universe is governed by equations derived by Alexander Friedmann in the 1920s. These equations come directly from Einstein's general relativity applied to a homogeneous and isotropic universe, one that looks the same in all directions and at all locations on large scales. The first Friedmann equation relates the expansion rate of the universe, called the Hubble parameter, to the density of matter and energy. It can be written in a simplified form. The square of the Hubble parameter equals 8/3 pi the gravitational constant time the density minus a term related to spatial curvature plus a term for the cosmological constant. For a flat universe where the spatial curvature is 0, the critical density equals 3 the Hubble parameter squared divided by 8 pi the gravitational constant. Now consider a sphere with radius equal to the Hubble length, the speed of light divided by the Hubble parameter. Calculate the mass inside this sphere using the critical density. Then calculate the Schwarzschild radius for this mass. The mathematics shows that the Schwarzschild radius equals the Hubble length if and only if the universe is spatially flat and has exactly the critical density. This is not a coincidence. It's a mathematical relationship built into the structure of Einstein's equations. The fact that our universe appears to be spatially flat with a density very close to critical means that the Schwarzschild radius naturally matches the Hubble radius. But this raises a question. Does this mean we're inside a black hole? In 1939, J. Robert Oppenheimer and his student Hartland Sonder published a paper describing the gravitational collapse of a spherical cloud of dust. This was the first realistic mathematical model of black hole formation. They made simplifying assumptions. The cloud was perfectly uniform in density. It had zero pressure. It was spherically symmetric. These assumptions allowed them to solve Einstein's equations exactly. What they found was striking. From the outside, an observer would see the cloud collapse until it formed an event horizon. From that point on, nothing that fell into the horizon could escape or send signals back out. The event horizon would mark the boundary of a black hole. But from inside the collapsing cloud, something different would happen. The matter would remain homogeneous. The spacetime would remain flat locally, at least until the matter reached extreme densities near the center. The interior could be described using the same Friedmann equations that describe our expanding universe, except running in reverse as a collapse instead of an expansion. This is where things get interesting. If you take the Oppenheimer-Sonder solution and imagine running time backward, you get something that resembles a universe. The collapsing black hole interior becomes an expanding universe interior. The singularity at the center toward which everything is falling becomes a singularity in the past from which everything emerged. In other words, the mathematics that describes the interior of a collapsing black hole can also describe an expanding universe. The two scenarios are related by a time reversal. This was the insight that physicist Raj Pathria explored in 1972 when he proposed his black hole cosmology hypothesis. What if our universe is the interior of a black hole embedded in some larger parent universe? From the inside, we would see an expanding homogeneous space. From the outside, if there is an outside, it would appear as a black hole. If a black hole's interior can look like an expanding universe, then what about the opposite? could an expanding universe look like a white hole? A white hole is the time-reversed version of a black hole. It's a mathematical solution to Einstein's equations that allows matter and light to emerge